Dr. Muhammad, and this is another video under the analysis of statically indeterminate structure. And I'm going to talk today about a new topic which is related to moment distribution method, and I'm going to talk today in this video only about definitions and terminology used in this method. So I hope that we can understand these definitions and the terminology related to the moment distribution, since it is important actually to give this intro or this introduction before going and indulging into the moment distribution method itself. Okay, now let's go to the introduction for our today's video. I would like to start with the some hints about this method, because really it is considered to be one of the most important methods in structure analysis in the history of structure analysis actually. And we can start with that this method, it is similar to the slope deflection method that I have explained in the previous few videos. They are the same in one thing, that they are suitable for continuous beams and frames. So like the slope deflection method, the moment distribution method can be used only for the analysis of continuous beams and frames, okay, taking into account their bending deformations. This means that any other types which is of structures that is involving axial deformations like bracing system, trusses, so they are not going to be suitable for it. Okay, they are not going to be suitable. We have said this limitation before when we were discussing about the slope deflection method. Okay, so this we need to keep it in our mind, that the method is only suitable for continuous beams and frames. What is the reason for this? Because it deals with bending deformations primarily, so or flexural strains and primarily. So this is why we are using it in continuous beams and frames. The method, which was initially developed by Hardy Cross, this is the developer of this method, and it was developed in 1924, was most widely used method for analysis of structures from 1930s when it was first published through 1960s. So it has been published like 1930. Before that 6 years Hardy Cross, he was working on it, and it was like the most widely, as you can see here, it's most widely used method from 1930 to 1960. So all of the people, they were working using this moment distribution method, and you are going to find and realize how much advancement that we have had in terms of matrix analysis and computer software and computer application that is going to save us a great deal of time when you look deeper to the moment distribution. And you are going to find how the people were suffering before in order to solve only a very simple continuous beam or a very simple frame. But anyway, this is how the history of structure analysis evolved. Since the early 1970s, this is actually the era or the start of the computer revolution in general. With the increasing availability of computers, the use of the moment distribution method has declined in favor of the computer-oriented matrix methods of structure analysis. And actually this is very true. What we are working now on using our computers and softwares, they are categorized under matrix methods, and it is very suitable to computers, and it is considered to be dominant in structure analysis in general. Okay, so this is for some hints about it. Something important also, that the moment distribution is still preferred by many engineers for analyzing smaller structures. So if you are facing smaller structure, actually moment distribution is going to be the best for you, because it will be quicker here and easy to implement, since it provides better insight into the behavior of structure. As you are going to see that really it's very nice method in terms of understanding the structural rigidity, stiffness, carryover moment, carryover factors. It's very important for any structural engineer to know about moment distribution, because it gives you an engineering sense and it adds to your engineering intuition. So this is why we insist on learning and teaching this method in our universities. It is used for preliminary, so we can use it, as we said, for smaller structures, and it is used also for preliminary designs as well as for checking. So now its use can be, we can say that it is under two main options, which is preliminary designs and checking. That is something good for the engineers to use. The main reason for the popularity of the moment distribution method in the pre-computer era was due to the fact that it does not involve solution or the solution of as many simultaneous equations as required by other classical methods. If you gone through what we have explained before, you're going to find that a lot of solution or simultaneous equations are needed to be solved. However, for other classical methods, as we have explained them before, okay? But for this one, you're going to find that it is an iterative method. You're not going to encounter solution of equations. Okay, it is iterative. It is based on an iterative nature. Okay. In the moment distribution method, the moment equilibrium equations of the joints are solved iteratively, and this is the key word here. That if you want to highlight the main keyword that is related to moment distribution, we can just say that it is iterative method, which is very appealing for and very attractive for the engineers. By successively considering the moment equilibrium at one joint at a time, while the remaining joints of the structure are assumed to be restrained against displacement. So this is how it works actually, and how the procedure itself goes based on iterative method, as we are going to see. Okay, now let's go to the next. We're going to talk about some definitions, very important definitions, as you're going to see, and some terminologies that are going to be important for us to understand the method. Let's start with the most important part of the definitions, which is the definition of the sign convention. We want to define our sign convention. So we are going to apply the same sign convention that we have used it in the slope deflection method. If you recall, or if you visit the video of the slope deflection method, the videos, you're going to find that we mentioned a very important sign convention rule, which is counterclockwise member end moments are considered positive. So whenever that we have anything that is counterclockwise, we are saying that it is positive. Okay, this means that clockwise is negative. Okay, so this is a very important sign convention that you need to take care of, and you need to think about it whenever that you apply the moment distribution. So whenever that you have a span, okay, if we have a span like this, okay, the end moments, we are talking always, take care, we are talking about the end moments. End moments of what? Member. So we are talking about, because you are going to find a lot of moments, okay? You're going to find moments and joints, for example. What we are giving the sign convention for here, it is related to the member end moments. So if we have a member like this, and we have end moment here and here, so the sign convention applies well, which is counterclockwise it is positive, and clockwise it is negative. Okay, so this is for what? Again, for member. Okay, but in most cases, in many cases, we are going to encounter moments on joints. So what should we do in this case? So let's go here and look to the case where that we have joints. Okay, if we have a joint like this, So the sign convention is going to be the opposite of the member. Okay, so if we're going to consider that there is a member here, for example, shortly we said that this one is going to be positive, right? If it is connected to a joint, so this one is going to be positive for the joint. And this one, this orientation or this sense is what? It is clockwise. So the negative for the joint is counterclockwise. However, the positive for the joint is clockwise. So it is opposite to the beam. Opposite to the beam. If we put the beam here, for example, this is the sign convention of the beam. But for the joint, it is the opposite. Remember that very well. Okay? So since a counterclockwise moment at an end of a member must act in the clockwise direction on the adjacent joint, the foregoing sign convention implies that the clockwise moments on, take care of this word, joints, are considered positive. So what should we do in order not to be mixed regarding this or confused? Remember this equation very well. Or remember, this sign convention that counterclockwise member end moments are considered positive. That's it. And then about the joints, it is the opposite. That's it. Okay, so remember what I have explained here because really it is crucial to understand this. Okay. Okay, now let's go to another definition which is important. We call this is the member stiffness. Member stiffness. Okay, in member stiffness, we're going to talk about, let's have this example so that we are going to understand what is the definition. Okay, let's assume that we have a beam that is fixed from one end and hinged from other end. Okay, and let's assume that we are going to apply a moment at this end, which is the hinged end. This M is the applied moment. And of course, whenever we apply the moment, there is theta, an angle that is going to be developed. Okay, so we have applied moment and we have theta, which is the resulting angle or rotational angle that is going to take place after the application of the moment. Okay, then we are going to define something related to the member itself. Okay, it is related to the member itself, which is the member stiffness or bending stiffness. Okay, we are talking here because we are talking about flexural, so it is understood that whenever we say member stiffness, it implies or it means that member flexural stiffness or bending stiffness. Okay, so we're talking here about the bending stiffness or flexure. They are the same. Okay, flexure. So they are synonyms here in this topic. Okay, we're not talking about anything axial. Okay, we're not talking about anything axial stiffness. Okay, so what is the definition of this? Let's go from this example or from this illustration. We're going to find that if I say to you, what is the moment that is needed in order to rotate this joint by 1 unit radian, for example, or 1 degree. Okay, so the moment that is going to be required in this case to rotate this point by an angle or rotation angle equals to the unity, this moment called the member bending stiffness. Okay, so we can't put it here and give it a definition, a clearer definition. So the bending stiffness, we call it like K bar, as you can see here. This is only kind of a sign or a letter that we put it for bending flexure or the member flexure stiffness. So the bending stiffness of a member is defined as the moment. So member flexural or bending stiffness, it is a moment in the first place. Okay, that must be applied at an end of a member or of the member to cause a unit rotation. Take care of this. Unit rotation of that end. So whenever we apply the moment here, whenever that we want a theta equal to 1 here, we need to apply a moment. We need to apply moment here. The magnitude of this moment is going to be the bending, we're going to call it the bending stiffness, or K bar. Okay? Okay. Now this is the meaning of the bending stiffness and its definition. We found something that is very nice, and it is related to the structure mechanics, that if we want to rotate this end, okay, this end, if we're going to rotate it for developing a unit rotation, we found that it is highly related to three main parameters. The first one, it is like function of the length of the member and the material of the member, which is, we can call it E of the material, Young's modulus of the material, whether it is a concrete beam or steel beam or wood or rubber or whatever. And in the same time, it is related to I, which is the inertia of the cross-section, or the inertia of the member that under consideration. So we found that it's function in these three parameters. So we are going to find that these are the main three parameters that is related to, or going to give us the bending moment. And we found something that is very interesting, that it's not only to the member itself and its length and material and inertia, but it is function also of the far end. Take care, I'm talking about the far end, not this end, not NA, I'm talking about B. We found that if the far end is going to be fixed, there is a value for this moment different than having the far end to be hinged. Okay, so the flexural stiffness of the element, okay, at this point, if the far end is going to be fixed, in this case, we found that K bar equals to 4 EI over L. As I said, it is function in three main parameters directly, EI over L. And this 4, if you want to say, it is coming from the boundary condition. Okay, so we have like three main parameters related to the element itself, and one parameter, or we can say a constant, that is related to the boundary condition. So now K bar equal to 4 EI over L if the far end of the member is fixed, as we can see here. So the moment that is going to be developed here is 4 EI over L. However, in this case, the far end is what? Hinged. We found that the moment that is going to be developed to make an angle rotation unit, 1 radian or 1 degree or 1 anything, it is a unit, 3 EI over L. This is the bending stiffness, which is here, 3 EI over L, if the far end of a member is hinged. Okay, so now this is the definition of the member stiffness. What I want you to understand is, which one is bigger, this one or this one? Seemingly we have a 4 constant here, everything is the same. Here we have 4, here we have 3. This means what? That the magnitude of the moment that I should apply in the case of having a far end hinged, if we have everything constant, E, I, and L, if the far end is hinged, I need to exert more or put more moment, which is 4 EI over L, compared to the case where that the far end is hinged, where that I should only apply 3 EI over L. 3 EI over L. Okay, so this means that my case of the far end, if the far end is fixed, the applied moment is going to be larger than the applied moment in the case of far end is hinged by 1/3. Okay, by 1/3. Can you imagine? So if we need, for example, if we need 30 kilonewton meter here, if we fix everything, EI and L, we need here 40 kilonewton in order to rotate it unit. Okay, unit rotation. Okay. This means what? And as I said, the moment distribution is going to provide you an insight into the the element itself. Now we are talking about the length, inertia, the material itself, Young's modulus, the boundary conditions. So it is going to give you sense. So if, for example, I say to you that you have two cases of beams, one far end is hinged and one the far end is fixed, and I applied, okay, if I want to, and they have the same EI over L, if I want to apply anything here, if I want to rotate both of them by a unit rotation, theta equal to 1 in every case, then I need here, for example, 40 something kilonewton. However, I need here only 30. This means that if the far end is fixed, I need to exert more energy, right? This is an intuition or something that you need to add to your understanding of the structure analysis. That fixation and the boundary condition, it makes some difference, especially for the bending stiffness of the structure. Okay, so this is what I want you to remember forever in your life for the structure analysis, that the bending or the member bending stiffness is function of its length, its inertia, the material, and the boundary condition. The far end is going to be fixed or hinged. Okay, now this is the member stiffness. Let's go to another thing, which is something very, very close to the member bending stiffness, which is the end moment theta relationship. They are the same actually with what we have explained before. We want to have a relation. What is the relation between the moment and the theta that is going to be developed? Okay, so we are having also two cases, far end fixed, far end hinged. Which one that we are going to apply? What is the relation here? It is very similar. Actually, K bar from the previous slide, it equals to M over theta. From where I got this? This is from the definition. Go to the definition. It is the moment that must be applied to an end member to cause a unit rotation. So K bar equals to moment over theta. Okay. So now we are going to put this here. You are going to find that the moment is going to be related with the theta using what? Exactly. It is K bar for it. So if we have the far end is fixed, as this case, so the moment that is going to be needed to rotate this into one unit rotation, it is going to be 4 EI over L times theta. And if the moment, if we are applying this to a case where the far end is hinged, then in this case, so the moment needed for making one unit rotation is going to be 3 EI over L times the unit rotation. Okay, so the applied end moment M and the rotation, this is the relation between the two. Okay, so this is very clear for us, and I hope that we can go. Okay, now we are going to talk about another definition, which is the relative bending stiffness. Okay, as we said, bending stiffness means that, yes, the bending stiffness, or before we were talking about bending stiffness, which is K bar. Now we're going to talk about relative bending stiffness. So relative bending stiffness, we call it only K. Okay? Relative bending stiffness. What is the meaning of it? When the modulus of elasticity of all the members of a structure is the same, this means that Young's modulus is constant, it is usually convenient to work with the relative bending stiffness. Relative bending stiffness is better because E is going to be cancelled in everywhere, right? So it is better to get rid of the inertia, which is E, and sometimes EI, the Young's modulus, and I, we call both as the inertia, so they are going to be cancelled in everywhere. So it is better, instead of using 4EI over L. Okay, we're going to get rid of 4EI. So we're going to like divide. Do you remember that K bar? It was 4EI over L. So I'm going to divide everything here by 4EI. 4E or 4E, sorry, not 4EI. It's only 4E. So we're going to 4E. It is going to be, cancel this 4E here and 4E in the denominator. So we're going to have E cancels E here, and the remaining is going to be 3 over 4, right? So the relative bending stiffness, which is K, of a member is obtained by dividing its bending stiffness, which is K bar, by 4I. So this would give us, after division by 4E, it is going to give us the relative bending stiffness, which is I over L if the far end of the member is what is fixed, and it is going to be fraction of it, which is 3 over 4 I over L if the far end member is hinged. If the far end member is hinged. This means that the relative bending stiffness is, if the far end is hinged, is fixed, it is I over L. However, if the far end is hinged, it is going to be 3/4 I over L. It is going to be 3/4 I over L. Okay? So now we have the definitions of main items. Let's go to another item here, which is related to the carryover. The carryover moment and carryover factors. What are these? The definition of these two important items. For our case here, the same example, or the same analogy that we are studying, or the same simple example that we are studying, which is related to a member with the far end is fixed or far end is hinged, as you can see. We found that something very interesting. Whenever there is the far end is fixed, we found that there is a moment that is going to be developed. We call it MBA. MBA. And this moment, just we are going to give it a title, a name. We're going to say this moment is the carryover moment. So this means whenever you apply moment here on point A or joint A, you're going to find that there is another moment is going to be developed here at the far end fixed, or the fixed far end. This carryover moment is going to be denoted as MBA. We found that this amount of moment, MBA, if the far end is fixed, it is half of this moment. So MBA equals to M over 2. What is M? It is the applied moment on this hinged end. It equals to M over 2 if far end member is fixed. So if it's here, it is fixed. And definitely if the moment here is going to be 0, if it's the far end is hinged, definitely the moment here is going to be what? MB. A is going to be 0. Right, that's very true. So this is the case for the hinge. We are going to find the moment, carryover moment is going to be 0. So this is what we call it, the carryover moment. The fraction, this is the definition of the carryover moment. The fraction of the applied moment M that is carried over to the far end of the beam. To the far end of the beam. Okay. If we apply the moment here like this, then here there would be carryover moment. Take care of their direction also. They are going to be in the same direction. The same direction. Okay, now let's go to the next part, which is the carryover factor. The carryover factor is very simple. It means that what is the fraction of the moment? What is the fraction? It is the same here. Instead of M here, we are going to divide this, the moment here, by the carryover moment by M. Then we're going to have half here. So this is what we call it, carryover factor. So the carryover factor for the case of the far end is fixed, it is half. However, that for the case of hinged, the carryover factor is going to be 0. The carryover factor is going to be 0. So what is the definition of the carryover factor? The ratio of the carryover moment to the applied moment, which is MBA over M. Okay, so MBA, it is what? The carryover moment, which is going to be developed at the far end, over M, is called the carryover factor of the member, called the carryover factor. Okay, so I hope that you can understand what is the meaning of the carryover moment, what is the meaning of the carryover factor. Now let's go to into the insight of what I have mentioned here. So I'm going to go back and forth to clean this up. So what is the meaning of this carryover factor and the carryover moment? The point is, if there is a kind of restraint at the point B, this means that it will attract some moment from the applied moment. That's the point here. So half of the moment is going to be transmitted to the far end. However, if the far end is hinged, nothing is going to be happen. Okay, this is why. What is the meaning of this? There is as if that there is a resistance would take place here. Resistance, okay, to the formation and the deformation, that there is some resistance at this far end or the fixed far end. Okay, this resistance means that it is going to be in the form of moment that is going to be developed. Okay. However, here, because this end, it is the moment here is released. There is no moment is going to be developed. This means that here carryover moment is going to be 0 and carryover factor is going to be 0. Okay, so you can remember that carryover moment, it is the resistance of the far end to the applied moment at the opposite end, or to on point A. Okay, now let's go to the next, which is very important. We call it the distribution factors. The distribution factors. Okay, now we need to understand first what is the meaning before going and indulging into this. Let's assume that we have something. Let me clean it up first. Yes, let's assume that we have something like this. That is like 3 spans beam, and it is the far end at point A is fixed, the far end at point D it is hinged, and at C it is fixed. Let's assume that every member, it has its length and inertia, as you can see, L1 I1, L3 I3, and L2 I2. And let's assume that I am going to apply a moment at point B here. I'm going to apply a moment, this moment called M. Okay, E is constant for all of them. So what will happen here? Whenever I apply the moment here, M, there would be some, exactly, resistance from the members. So there would be resistance from here, and there would be some resistance from here, and there would be some resistance from here. Take care that all of them, they are in the same sense. They are counterclockwise. Why? Because the applied moment is clockwise. We need to reach equilibrium at point B. This means that the resisting moments are going to be in opposite direction of the applied moment, and they are going to have the summation of these resisting moments is going to be equal to M, which is the applied moment, in order to maintain equilibrium at point B. Well, that's very nice. So if we look deeper to this, we're going to find that this is the joint here. What will happen is the resistance from each member is going to be contributed here. We are going to have M. So I think that there is, yes. Actually here we put only the sign convention without considering the sign convention that is being put here. It is not considering the equilibrium of this B. So it's better to go with my annotation, which is this annotation as I put it here. So there is moment that is going to be developed, which is different or opposite to the applied moment. what is the value of each moment that is going to be developed? So first of all, we have member BD. The far end is what? Hinged. And there is theta that is going to be developed here. Okay. Actually, in order only to know what's happening here is they are putting like as if this is the result of M. So this is like the action. However, the reaction is here on the members. Okay, so the reaction is going to be similar to my sign convention that I put, because if you remember, I put that something here, something here, something here. They are, all of them, they are counterclockwise, which is, as you can see, all of them here, counterclockwise, counterclockwise, counterclockwise. But these here, around the joint, these are the actions, which is opposite to this, okay? So we are studying from the beam standpoint, from the beam point of view, okay? So now, let's go back. So the beam is going to resist this moment, okay? Resist this moment. Every beam is going to develop the amount of moment, the magnitude of moment that is related to theta. Take care that theta, because we are talking about the same point and the same moment applied. So theta of member BD, it is going to be the same for theta for member BC, going equal to theta for member BA. Okay, so we have the same theta. Why? Because it's the same point and the same moment. Okay? Okay, now, this theta is going to develop moment, which is MBD and member BD. What is the magnitude of this moment? It is going to be function of the boundary condition, which is hinged. So we have 3 here. And EI3 over L3, because we are talking about member 3. Okay. And what about the other one here? There is moment that is going to be developed for member BA, and this amount of moment, or the magnitude, is going to be function of the far end, which is fixed. So we have 4 here, EI1 over L1, because we're talking about member 1. In a similar fashion, MBC, it is going to be counterclockwise, and the magnitude, because here, this is the far end here, is what? Fixed. So we have 4, as we explained before. And then we have EI2 over L2, which is the member characteristics. Okay, the member characteristics. Okay, so now what is the meaning of distribution factor at the end? What I want to say, what should I say here? So if you understand what I'm saying here, implicitly you have understood what is the meaning of distribution factor. The point is, this moment is going to be distributed among the 3 members. The moment is going to be distributed among the 3 members. The resistance of this moment is going to be distributed among 3 members. So we want to know how much, what is the fraction of the moment that is going to be carried by this member, and how fraction is going to be used here, and what is the fraction that is going to be used here. So this is the meaning of the distribution factor. Now it leads us to the definition directly. The distribution factor is the ratio of the relative bending stiffness. We said what is the meaning of relative bending stiffness, okay? Of the member to the sum of the relative bending stiffnesses framing into the same joint, okay? So the ratio of the bending stiffness of the member to the sum of the relative bending stiffness, okay, of all of the stiffnesses framing into the same joint. Okay, this means what? Okay, first of all, this M, it equals to what? The contribution of all elements here, which are all spans, 4EI 1 over L1 and 4EI 2 over L2 and 3EI 3 over L3 times theta, right? Moment equal to the relative stiffness of all of them, the bending stiffnesses, times theta. It is already from the previous equation in the previous slide, right? This is the bending stiffness times theta equals to the moment. And this bending stiffness for each member is given here. What is this? It is the bending stiffness K bar BA. plus K bar BC plus K bar BD times theta. If we are going to collect all of them, they are going to be summation of K bar. So we can say, now, if I want to have the fraction of MBA with respect to M, I want to know how much MBA is going to resist from M. So it is going to be simply KBA, which is 4EI1 over L1 over the summation of all stiffnesses around this point B. We have 3 stiffnesses here, right? All of them. So it is going to be like this. MBA is going to be KBA over the summation of KB. Similarly, for MBC, it is going to be KBC over the summation of the relative stiffnesses at point B. We are talking about point B here. So this is why we call it KB. KB means that all relative stiffnesses. And here for KMBD, it is going to be KBD over the summation of the relative stiffnesses. Okay. This is what we call it here, the ratio of the moment with respect to the applied moment. Okay. Then, where is the distribution factor here? It is going to be shown to us here. This value here, which is KBA over summation of KBE, we call it distribution factor related to the member BA. Okay, the distribution factor of member BA. And this one here, this fraction, it is the distribution factor for member BC. And here, this is going to be the distribution factor for member BD. Okay? This is what we call it the distribution factors. This is what we call it the So the distribution factor simply is K over the summation of K. So if I have, for example, if I have like something like this, and we have different ends here, okay, then if I'm going to talk about this point, I will have an applied some moment here like this. I will have 1, 2, 3, 4 different distribution factors representing every member framing into the same point. Okay, what is the summation of the distribution factors? They should be 1. They should be 1. So now let's read this. The applied moment M is distributed to the 3 members in proportion to their relative bending stiffness. The ratio K over summation of KB for a member is termed distribution factor, as I said, this one. This is considered to be what? The distribution factor of that member for NB. And it represents the fraction of the applied moment, this is its definition, the fraction of the applied moment M that is distributed to NB of the member. Okay? So that's the meaning of the distribution factor, and this is the issue regarding it. Okay, the last thing that I want to highlight here is the fixed end moments. The fixed end moments, as you know, expressions for some common types of loading conditions. It is going to be found in the back cover of the book. We already have mentioned this in the Slope-Deflection Method, so you can find it in the back cover of the book. We are using the Aslam Kasamali 4th edition, so you can find this in the course description. In the moment distribution method, the effect of joint translations due to support settlements and side sway are also taken into account by means of fixed end moments. Actually, we didn't mention about this, or we have put it, you are going to find it also in the fixed end moments. Fixed end moments commonly are formed due to external loading. But whenever there is external or support settlement, there is a kind of fixed end moment that is going to be developed. So here, for example, if this is delta, that is the settlement of a fixed beam that is going to take place here. This delta, if we say that it's 1, then the moment that is going to be developed, it is going to be counterclockwise moment, as you can see here, and its magnitude is going to be 6EI delta over L squared. However, if the settlement was on this point, which is point or joint A, it is going to be the same magnitude. However, the sense is going to be clockwise. Okay, so here it is counterclockwise, here it is clockwise. Okay. Okay, that's it for today's video. I want to recap what I have explained here. Very, very important definitions. I want to highlight them. First of all, the sign convention, remember that well. Positive, counterclockwise, we are talking about member end moments. The opposite would apply for joints. Member stiffness, it is going to be 4EI over L if the far end is fixed, and 3EI over L if it's the far end is hinged. In moment relation, it is going to be the same. M equals to K bar times theta, which is 4EI over L in case of fixed, or 3EI over L, which is K bar times theta for hinged. The relative bending stiffness, commonly we use it whenever that we are having the same E. It is simply equals to I over L if the far end is fixed, 3 over 4 I over L if the member is hinged. And the carryover factor and carryover moment is the amount of moment that is going to be taken whenever that we apply it on one end. We found that the carryover factor, the carryover moment, is half of the applied moment if the far end is fixed, and it is 0 if the far end is hinged. And we found that the carryover factor is going to be the fraction that we're talking about. Half for fixed, 0 for hinged. I mean that for the far end. Okay? And then the distribution factors, we said that it is the ratio of the relative bending stiffness of the member, okay, that is going to be developed to resist the moment. So what is the distribution factor is? Simply, it is the relative bending stiffness over the summation of all relative bending stiffnesses framing into the point itself. Okay? And the last thing, that the summation of distribution factor should equal to 1. And the bending fixed end moments, you can find it in the back cover. This is the summary of what I have said for today's video. Thank you very much for listening, and see you in the next video.